Good morning. Welcome. I'm going to introduce Daniel Keller. He's the first of the Graduate Student Summer Speaker Series as part of the Graduate School of Arts and Sciences. And welcome, Daniel, and I'm going to turn it over to you.
Thanks for the introduction. So I'll be talking about number fields, symmetries, and counting problems. All things I'll try to introduce as I go. I'll just say that sort of number fields are the objects of interest to me, and I'll try to motivate them with symmetries. And then as a number theorist, really all I do all day is count things pretentiously, so hence counting problems. And then I'll also just say that the actual parts of my work that will make an appearance today are all joint work with Matt Fredrickson, who is another grad student at Tufts. So we'll start just at the very beginning of the story, which really starts with a problem motivated by questions asked, like in antiquity, just what are the solutions to polynomial equations? And it turns out this is a very hard problem, which I mean, in general, one could arguably say that we've made almost no progress on. So our running example today, which we'll just kind of keep with us as we go, is just x squared minus 2, right? So this is something that you would have seen in grade school or something. It factors like x minus root 2 times x plus root 2. And so its solutions are just plus and minus the square root of 2, right? You didn't even need the quadratic formula. You could just look at it and you knew what the solutions were. So this is what we're going to kind of hold with us as we go. But in the back of your mind, you should think, okay, well, I could tell the same story with a more complicated equation where I couldn't just look at it and know what the solutions were. And you should notice that we had to use the square root of 2 to write down this factorization here. And maybe that's upsetting to you. Maybe it's not. It's upsetting to me. So we're going to introduce some auxiliary structure to sort of make sense of why we had to do that. So the first thing we're going to do is we're going to consider maps that exchange roots of the polynomial, right? So you had this polynomial, x squared minus 2, and you factored it like this. And then we're just going to exchange, consider maps, which literally just rewrite this equation by exchanging the roots by the red root and the blue root, right? So the first map that you can think of is just, I'll call the do nothing map. It takes the blue square root of 2 and sends it to the blue square root of 2, and the minus root 2 and sends it to the minus root 2. So that's sort of the most obvious map. And then the other admissible map that we have is what I'll call the swap map. And the swap map just takes positive square root of 2 and sends it to minus square root of 2, and takes minus square root of 2 and sends it to plus square root of 2. So let's apply these maps just to the equation that we've had written. So here's x squared minus 2 factored. And I've just arbitrarily decided to write the factors in this order. It doesn't matter what decision you make here. So I've just decided to do it this way. So if we apply the do nothing map, well, the red root stays where it is, right? And the blue root stays where it is. And then you factor it back together at the end, or you multiply it back together at the end, rather, and you get x squared minus 2, right? So you get back what you started with, but you sort of did some intermediary step, and you swap the roots. So what does the swap map do? Well, the swap map does exactly the opposite. It takes the red root and sends it to the blue root, and it sends the blue root and takes it to the red root. But then if you multiply things back together at the end, you get x squared minus 2, which was the polynomial equation you started with. So we can think of these maps as the symmetries of the polynomial. You can sort of shuffle the individual terms around, but then when you multiply all those terms back together at the end, you still get the equation that you started with, in this case, x squared minus 2. So these are just, we call them the symmetries. But you can imagine that if you had written down a much more complicated equation and then you had tried to define a rule, say like the swap rule or something, to do something to the polynomial, you could then multiply things back together and not get the equation you started with. So we don't want to admit these maps into our classification of symmetries. So, I mean, you can go try this at home and write down some complicated thing and then try to define maps on it, and you'll find some that just don't work, right? By don't work, I just mean that when you multiply things back together at the end, you don't get x squared minus 2. So it's maybe not clear what this helps you do at all. And in fact, just this perspective helps you do very little. So we need to introduce something more general that has more structure that we can actually work with, and that way we can answer interesting questions about polynomials, or questions that I think are interesting anyway. So I'm just going to have some definitions here. So every time you see this blackboard face Q, it's just going to mean the field of rational numbers. Right? And this has a very precise meaning, but you can just imagine the collection of all fractions. That's fine. In particular, it doesn't contain things like the square root of 2 or I or like it doesn't contain anything funny like that. It just contains like the fractions that you know and love from grade school and have a good intuition for. So just every time you see this q, I just mean the collection of fractions. And the sort of salient feature of q is that you can add, subtract, multiply, and divide as usual in q, and you never escape q by doing so. The point being that if you take two rational numbers and you multiply them together, you get another rational number. Or if you take two rational numbers and you add them together, you get another rational number. That's what I mean by you never escape q by performing any of these operations. And these nice properties, these nice arithmetic properties, make q into this object we call the field. And your intuition about how arithmetic works is that all works in an object called a field. So right, if you try to do like simple arithmetic operations in Q, right, they work like you think they work because, well, you know how to manipulate fractions. And then any other time I say field, well, you can just fall back on that intuition and it will work. So our first goal is going to be to build, in some sense, what a bigger field that contains information about polynomial equations. In this case, I mean contains information about x squared minus 2 equals 0, this running example that we're going to have. And what you should notice at the outset is that the solutions of x squared minus 2 equals 0, namely plus and minus the square root of 2, don't live inside Q at all. And so this is something we need to remedy by building a better field or a bigger field. So let's do that. So let Q adjoin the square root of 2. That's how I'll read this collection of symbols here. Q adjoin the square root of 2 is going to be the collection of numbers of the form a plus b times the square root of 2, where a and b are rational numbers. So things that are examples of members of this Q adjoin the square root of 2 thing are a half plus 3 times the square root of 2. That's a perfectly good number, and we'll say it's in there. Or minus 12 plus 4 ninths times the square root of 2, another perfectly good, albeit kind of weird looking number, but it's in there. And we want to consider the collection of things that look like that. And it turns out that Q has nice arithmetic. You can add and multiply and subtract and divide. And all those operations, they work in the obvious way. Maybe the only one that isn't sort of clear if you mess around with it for a few minutes on your own is how division works. But I sort of promise you, if you try to write down some division and try to do it, and you futz around with the algebra for long enough, it'll work out. And all of the nice properties that arithmetic of the rationals have carries over to Q adjoin the square root of 2. So you can do algebra in there in sort of the same way that you do algebra with fractions. So Q adjoin the square root of 2, this thing, is called a number field. It's one example of a number field. And in some sense, we're going to just say that it lies above Q. It lives above Q. My choice for this phrase will hopefully be clear in a few minutes when I draw some pictures. But the other thing to think about is just that Q lives inside here just as a set of things, right? If you look at the form of numbers a plus b times the square root of 2, well, if you set b equal to 0, and then you let a arrange over all rational numbers, well, you've ranged over all of Q, and so Q lives inside Q adjoin the square root of 2. And then the other thing to notice that's important, and in some sense is the point, is that the roots of x squared minus 2, this polynomial example we're going to keep beating to death, is they live inside Q adjoin the square root of 2, just by definition. So the takeaway here is that every polynomial equation determines some number field that contains information about solutions of the polynomial. So instead of thinking about a polynomial, we can go over to this other world where we can think about a number field. And then the salient features of the number field, the point rather, is that it has additional structure that lets you do stuff. And so I just want to take a brief aside and maybe answer the probably burning question that you all have, is why bother with any of this? So let me try to justify why this isn't all just empty philosophizing. So the easiest example of this is that for quadratic equations, things that look like this, or things that look like x squared minus 2, or have a leading x squared, the quadratic formula, which we all learned about in middle school or something, which dates back to antiquity, tells you the solutions, right? As input, it takes the equation, and as output, it tells you the solutions to the equation with a nice formula. It turns out that for cubic equations, there's a similar thing. There's a formula which takes as input your polynomial, and as output tells you how to find the solutions. This is called Cardano's formula. It dates to, or the first published version of this was in 1545. And actually in the same book where Cardano's formula was published was a solution for quartic equations. So things with a leading x to the 4th instead of a leading x cubed. Maybe I shouldn't call this one a formula because it's really a procedure, but it takes in as input the polynomial, and as output tells you all the solutions to the polynomial, which is pretty cool. And these two things actually have a really rich and kind of amusing history. It turns out that Cardano's student published the solution for the quartic, but it relied on the solution to the cubic. So they ended up publishing them together in the same book. But it turns out Cardano may not have actually come up with this solution. Another Italian mathematician also claimed credit for it around 1545, and it led to a 10-year feud between them where they exchanged really angry poetry with each other for about 10 years. But we still call it Cardano's formula. And then the really important point is that for quintic equations, so things that have a leading x to the fifth, or anything more complicated, in general, there's provably no formula that tells you the solutions, right? There's no like nice equation that you can write down where you can feed it as input this formula and it spits out what the solutions are. You can prove that no such thing exists. And this came about in 1824 following work of Ruffini and Abel. This also has a really interesting story. The sort of first steps towards it were taken by Évariste Galois in the several years before 1824, but he didn't finish writing down his solution because he died in a duel. So there's actually a fascinating history to all of these things, but the main point is that the ideas that underlie to all these proofs can be expressed really elegantly in the language of number fields and the stuff called Galois theory, which I'll talk about or at least hint at in a little bit. So this stuff is useful. It's good for proving that there aren't formulas that solve quintics. For example, they have a rich theory beyond that, which I won't really get into, but hopefully this justifies my existence a little bit. So let's get back to the number field story. And so one really interesting thing we can do is we can make sense of those symmetries of polynomials as maps on number fields. So right, remember at the very start, we were talking about symmetries of x squared minus 2. We had like the do nothing map and the swap map, which just exchange terms of the polynomial when you wrote it down in a nice factored way. And we can make sense of that as a map that takes stuff from q adjoin the square root of 2 and sends it to q adjoin the square root of 2. So it's just a rule that takes stuff in one sort of copy of q adjoin the square root of 2 and tells you how to identify it to something in another copy. And it does so by taking the do nothing map. So perhaps unsurprisingly, the do nothing map takes a plus b times the square root of 2 and then sends it over to a plus b times the square root of 2. It just does nothing to the elements. And then the swap map is a little more complicated, but is still maybe not so surprising how it acts on q adjoin the square root of 2, right? You just take an element, a plus b times the square root of 2, and you send it over to a minus b times the square root of 2. Very roughly speaking, and I'm sweeping a lot of theory under the rug, but that's sort of okay for the purposes of what I want to say later. The data of how these maps, the do nothing map and the swap map, or whatever analogous map you have for some polynomial, the data of those maps and how they act on the relevant number field, in this case q adjoin the square root of 2, is called the Galois group of the number field. And so the main idea that you should really take away from all this is that if you want to think about questions sort of in the world of polynomials where you can think about their symmetries, well, you can translate any question you have over there to a question about number fields and their attached Galois groups. And this, it turns out, for a variety of reasons, is really advantageous. In particular, the theory of number fields is very rich and deep, and number theorists have been thinking about it for a long time. And so there's a lot more tools and structure over there that can help you answer your question from the polynomial world. Okay, so now what? We have these polynomial equations. We've gone through all of this work of defining number fields and Galois groups. So what should we do with them? Well, like any good mathematician, we have things, and so we should count them and see how many there are. That's sort of one of the most fundamental aspects of structure is if you define a thing, you should know how many of those things you have. So let's just address the question, how many number fields are there? Well, this is, it turns out, not a great question. There are infinitely many. Here's 5, and you could sort of proceed in this way forever. All of these number fields, so q adjoin the square root of 2, likewise q adjoin the square root of 3, these are all defined in the same way that we define q adjoin the square root of 2, except rather than tell the story with x squared minus 2, you would tell the story with x squared minus 3, or x squared minus 5, or x squared minus 7. So there's just a, I could have this whole talk could have been rephrased in terms of x squared minus 3, and we would have started our discussions just with q adjoin the square root of 3. But I'm getting ahead of myself. The point is there's infinitely many, so this isn't a great question. So maybe we can refine the question a little bit, and we can ask, well, how many Galois fields, sorry, how many number fields are there, but with a specified Galois group, so some specified structure. So maybe you know what kind of maps you want to have acting on your number field. So you specify in advance the sort of Galois data that you want to have, and now you want to ask, okay, how many number fields have that property? Turns out this is also not a great question. There are still infinitely many. And so we need to introduce something that will let us refine the question a little bit. So to do this, we want to sort of cook up some reasonable way to organize number fields. And it turns out this is actually, there are a number of ways to do this. I'm just going to pick one because if I pick this way, I can prove things. But there's a number of ways to do it. And it turns out that you can very systematically assign what I'm going to call a height to every number field by attaching to it a gadget called the discriminant, which is just a number. The discriminant, it doesn't really matter what it is. For our purposes, it's just a number that is going to let us organize things by their height. But I should mention that this discriminant thing it has many really nice properties which tell you a lot of very interesting things about the arithmetic of the number field you attach it to. So interesting to number theorists for a number of reasons, independent of this height business. But we're going to use this height to ask what I claim is a better question, namely how many number fields are there with specified Galois data, but now with height less than x, right? So if we don't bound the height, then we get infinitely many things. So what we're going to do is we're going to cut off at some height and then count things below that height. So here's sort of a doodle of what I mean. Here's a bunch of number fields. They all live above q in some sense, namely they all contain q. And then below them, I've written their discriminant, so their height. So you can imagine just there's an infinite collection of number fields sitting above q, but I've now organized them all on sort of the d axis by their height. And so now the question we're going to ask is, well, if we fix a number x, and then can you count all the number fields living below x? So in this picture, that corresponds to how many fields on the picture live below this red dotted line. I should just say this picture is very crude. There are many more number fields on this picture that should be on the picture than I've drawn, but hopefully this conveys the idea of what I'm trying to say. So we have this new and hopefully better question. How many number fields are there with a specified Galois group and some height less than x, right? So we're just trying to count things below the red dotted line. So this is hopefully a pretty concrete feeling question, even if it's sort of couched in the language of this sort of untethered abstraction nonsense. There are many partial answers to this question. This question, it turns out, is really hard. So for certain degrees and certain Galois groups, you can say some things, but phrased just as we phrased it as a very general question where we haven't really placed any limitations besides some Galois data on the number field, we really haven't made much progress on this at all. And this is sort of a question that's, well, various progress has been made since the early 1900s, but recently number theorists have really been taking a serious attempt at trying to figure out what's going on here. And still not a huge amount of progress has been made. So one thing that will hopefully convince you that this question is actually reasonable or interesting is that for a fixed x, the number is always finite. So now when I say let's count things, the number that you count will be just some number and not infinity. So hopefully that makes it interesting. So now I just want to, in the last few minutes, just depart from this world of x squared minus 2 and q adjoin the square root of 2 and ask you to take a few things on faith so I can state some results and tell you why they're interesting. So I'm going to let this n subscript degree superscript base field of Galois group in x. This is just going to be the collection of symbols I use to count things. So whenever you see that, it's just counting the number of number fields with some Galois group and height less than x. So it's just the number of things that I'm interested in. And our examples so far, namely q adjoin the square root of 2, has been degree 2, and that's just because the number field was determined by a quadratic equation, by x squared minus 2. So for the rest of our discussion, we're going to talk about number fields of degree 4. The story is essentially the same for those. They're just they're a little bit more complicated to write down, but the idea is that they're just number fields determined by polynomials like x to the 4th minus whatever. So things that look like this that have a leading x to the 4th in them. But I promise the story is the same. It's just harder and more cumbersome to write down all the details. And then finally, so far, all of our base fields have been living above Q, right? They all contain Q in some sense. They all contain the rationals. But nothing stops you from imagining these number fields living over something else. Maybe you want to think only about number fields which live over Q adjoining the square root of 2, so which contain Q adjoining the square root of 2, right? So in the picture that we put up earlier, right, that would just mean that instead of Q being at the bottom, Q adjoining the square root of 2 would be at the bottom. It's probably not clear why you would want to do this. And in fact, I don't even know that it's clear to me why this is more interesting than doing things over Q, but it actually lets you get some interesting numerical results. So the answer to the question, why bother, is because I can, and something interesting happens. So we're going to live in this degree 4 world now. So the most prevalent Galois groups you can have are S4 and D4, right? So I'm not going to say what these are. You can just think of them as two labels. So we can sort all of our degree 4 number fields as fitting into two camps, the S4 camp and the D4 camp. There are other possible labels, but they're extremely rare, and they're provably extremely rare. And this was proved in the 50s that really these are the only two labels we need to worry about. So it turns out, and I should just mention this for culture, I guess, is that under a different method of organization, not this height method that I've been talking about, 100% of number fields have the S4 label. And the very vague intuition for this is that S4 is a stand-in for saying that the symmetries of the polynomial can be whatever they want to be. You can just exchange those terms that we had been writing down before with complete impunity and never go wrong. And maybe it's very believable that you should be able to do this, that there shouldn't be limitations on this sort of thing, or those limitations should be rare. That turns out to not quite be right for this following reason. So if we return now to organizing number fields in the way we were talking about before, namely by height, corresponding to that picture that we had put up, work of Bargava combined with work of Cohen, Diaz, and Olivier says the following. And it says that about 83% of degree 4 number fields above Q have an S4 label, while about 17% have a D4 label. So put into symbols, right, remember this expression is just counting degree 4 things above Q, which have the S4 label. And then if we just divide by the number of things that have any label, we get about 83%. The reason for this limit x to infinity is that the formula we have for doing any of these enumerations are really only sensitive or accurate feeling when x is very large. They're all asymptotic. So if you ask how many number fields are there with like height less than like 15, I can't give you a very good answer without just looking for them by hand. But if you ask for really, really large x, I can give you a good answer. And of course, we can change this Q here. Remember, this is the thing that we're thinking about our number of fields living over. We can change that to be any field we want. So we could change it to be Q adjoining the square root of 2, for example. And so the question that Matt and I are interested in is that can you manipulate these percentages? Can you manipulate this 83% and 17% by changing this Q to be something else? And it turns out, yes. So what we prove is that if you look over all degree 2 number fields, so all things that look like Q adjoining the square root of 2, or things analogously defined, if you look over all of those and then you consider the ratio of the number of things with an D4 label to an S4 label, this whole expression tends to infinity. And said differently, what that means is you can find F, where if you look at the degree 4 things above F, you can find examples of F that are skewed to have as many more D4 labels sitting above them than S4 labels. You can actually take these percentages, 83 and 17, and skew them as much as you want in favor of this expression over here. And this is kind of surprising, right? Because it's completely flipping the story over the alternative method of computing height and completely flipping the story over what is true over Q. And so I think the most interesting rephrasing of this expression is just that it's true that for 100% of number fields, of degree 2 number fields F, arbitrarily many more of them have, or rather 100% of them, arbitrarily many more have a degree 4, have degree 4s over them that have an S4 label than a D4 label. So you can flip the story around as much as you want, which I think is really interesting and is not what is true over Q, and is certainly not what matter I would have guessed when we started this. Okay, I think I'll stop there. Thank you.
Thank you, Daniel. That was awesome. Does anyone have any questions for Daniel? You can either ask them in the chat or you can unmute yourself.
Yeah, I have a question. Thanks, Daniel, by the way. So I was wondering, just can you explain a little bit about how, with the original example of how you count based on height and the, some other method of counting, you can have 100% of things falling in, I think it was the S4 category, versus when you count by height, it's no longer 100%. I don't quite understand that.
Right, so what you could just sort of imagine is, so the intuition I'm going to give you is a little bit flawed because we're talking about like things which contain infinitely many objects. But you could just sort of imagine that maybe all of your, in the method of organizing by height, for example, maybe all of your D4 things live really high, sort of in this height analogy. But then in an alternative method of sorting, you can imagine all of them having really low height or something. So what you're sort of observing is that these methods of organizing are actually very arbitrary. And so it just kind of works out that way. I don't know if that's not a very satisfying answer to your question. I'm sorry.
I mean, tell me if this is right. So is it kind of like that in one method of organizing, maybe, the fraction of fields that have some label sort of asymptotes to 100%?
Yes, exactly.
And then, there is some number of the other category, but in this method of organizing, they're sort of tucked away.
Yeah, exactly.
Okay.
That's a good way of thinking about it.
Thank you. Great talk.
Are there any other questions?
Yeah, I have a question about the base field. So your result is for base field of degree 2.
Mm-hmm.
And have you tried some other base fields?
Yeah, we actually have a result which works for base fields of any degree, and gives bounds on that ratio, gives bounds on this ratio. But in order to give them, we need to assume the generalized Riemann hypothesis. So,
okay.
Which is true, but
yeah,
reviewers don't like that.
Mm-hmm.
We're just about at time. So if there are any other questions, I'm sure that you can email Daniel directly. But we really appreciate your time, and this session will be recorded. If you'd like to see it or share it with your friends, we'll be sure to disseminate that link to you.
Thanks. Thank you all for coming.
Thank you.